Hello, I'm Dhananjay, and I found some minor and major boundaries in the circuit for key generation and all the four circuits. I forked this repository, and I'll walk you through the bugs and minor bugs that I've found, also the major bugs and some fixes as well. So, looking here, this is a state 3 depth. So now, initially we had this check which used to check if it is a greater than zero value, but this is a finite field. We need to keep it in a finite field. So what we do here is put it inside this assert to make the tree depth to less than 32. It can be any value, but it has to be uh, less than the value of the finite circuit. Now let's move to some, I would name this as a minor bug. Now, what is that? This is this lies in between the major and the minor bug. So the fix here is the problem here is we are using a hard-coded nullifier. So what this would have mean that you could see that I'm setting the nullifier hasher's right pointer to this hard-coded value, which we treat as a nullifier. But we can't do that because now the user or the attacker knows that this is a hard-coded value, so he can just point it towards them, and this creates a kind of a vulnerability system, making it very predictable. So what I provide a fix is we can keep it more dynamic. So as in user can provide a hard-coded nullifier within the circuit as a signal input. So he provides the signal inputs nullifier salt, which is like a dynamic salt for improving security and flexibility. So now there is no hard-coded and predictable values, but it is all coming from the signal input from the user itself who is generating this proof. And yeah, this is the major, like a major bug in this circuit. What it is initially it was like this. So we, if you look at this, let me just go up. Let me just go up more. So when we take signal input, we take input for two components. For D1 we have two components, for D2 we have two components. But if you go down and if you check the re-randomization ciphertext, we just check for first component and we don't do that for the second component for both these signal inputs. But whereas we take it for both the inputs. So we can uh, fix this by just like checking it for the both the components, not just the one component, because we want to cater to both components. And yeah, so this was the fix for this circuit. Let's move to the next circuit. So again, this is the same thing where we just have to keep it in a finite circuit. So it is greater than zero, but it should also be less than equal to the state 3 depth that you think should be kept the maximum threshold for so that it doesn't exceed. Okay, this one. So this is basically initially we had the index to be less than equals to 252 because it is again has to be kept in a finite circuit. And if we don't uh, have a checksum, like check before the number input, then it would obviously cause errors and vulnerabilities in this circuit. Moving on, and I'm not naming this as a minor or major, but I'm not sure it would be somewhere around a minor thing to say. Okay, okay, so this is like a major thing where we are capturing the string is empty or not after we do all this computation. Computation is done on the encrypted public key and encrypted private key, like encrypted public keys of two components on the message hasher. So now Once it is done, only then we check the empty message. But if it is empty beforehand, then this would give us an error. So we have, if we just move this here, say, then this would mean that we don't have to again write the same logic, and like we don't have to do computation, and it won't result to an error in the future.